Welcome, everybody. Oh, that's louder than I was suspecting. Welcome. I'd like to introduce myself. I am Matt Kelly. I am from TripAdvisor. I've been at TripAdvisor now for about 5 years, so about a third of the company's life. But about 18 months or 18 to 24 months ago now, I swapped from just being, normal application developer at TripAdvisor to being the company's Postgres expert. And I'm very glad to be here and give this talk because TripAdvisor really loves Postgres. It is a major part of our core infrastructure all the way across our stack, and we're trying to get more involved in the community. So Postgres has grown up with us, even back from, I'm trying to remember, I wasn't even there, obviously, back from 7.4 series back in 2000, where that room up there was the entire T of TripAdvisor. We were a little startup, to our current brand new headquarters, which seats 1,500 people. So what are we actually building at our company? Well, pulling off just stupid fact sheet, we've got about 290 million pieces of user-submitted content, and running 47 different points of sale, site translated. I think that's 35 different languages or somewhere around there. 500,000 hotel, millions and millions of locations, and as well as sustaining a site that does about 350 million unique visitors a month. At peak, that ends up translating, we've seen north of 2 million HTTP requests a minute. So I want to make a pretty strong statement, especially for the people who are starting to be new into the Postgres community. Postgres, with a tiny little caveat at the end, Postgres is the only database serving the TripAdvisor website full stop. We used to have a little bit of Couchbase, and we played with some other things, but Postgres has been the one thing that we've been able to use reliably as a core piece of our infrastructure at scale. My caveats is we like a lot of flat files, both log files and data files, and our site is architected very heavily to protect our databases. That way they can be a system of record, and we still have to use a little bit of Elasticsearch, not as the master of data, but it turns out doing APAC languages is a little bit hard for search and type ahead if you can't do tokenization, and Elasticsearch handles that. Trip in the Postgres community. We're definitely trying to improve our relationship with the Postgres community and put some more effort into it. We think we have something to offer to the community because we push our databases really, really hard, and we end up finding breaking points that only the people on the edge end up doing that. And we also want to be more open about what we're talking about to instill some confidence in the newer members of the community that that Postgres works well at scale. And the only reason we haven't done as much as we'd want to is we're slightly understaffed at the moment. I had some more goals of what I was going to do with the community this year, and they just kept getting backburnered. Here's my shameless hiring plug. So what does operations look like at TripAdvisor? So I said we're running a site that does 350 million uniques a month. So our operations team is broken into 3 main categories. We've got our tech ops, which does OS, networking, hardware stack, et cetera. And they maintain our 4 main data centers and somewhere around 5,000, 6,000 pieces of equipment, as well as doing a lot of, we have our own WAN and backbone across the world. We carry a lot of our own network traffic across the country and back and forth, and they maintain all of that. Our Postgres operations basically amounts to me full-time and my boss half-time because he's managing like 3 other teams. And then site operations, which gets about everything else. In fact, if we go even further back before I started, at one point, site operations was 3 people, and there was no one on Postgres. Postgres was just collectively owned by our operations team. And I think it's a major credit to Postgres that was able to withstand cases where there wasn't even anyone dedicated to focusing on it. We run our operations a little bit different than a lot of companies. With the exception of 2 or 3 people on the tech ops team, everyone in our operations team is a software engineer. In fact, very large numbers. Site operations, I think everyone, 3 or 4 of the site operations team members were principal engineers on their teams before they switched over. I switched over from an application team as well. And so our operations team is incredibly involved in our design review process. It's pretty common for me to just go to the general bi-weekly engineering design reviews. People come by my desk all the time. And so unlike a lot of companies where there's this barrier between operations and engineering, there is a very tight relationship between our engineering and operations team. And we've had cases where a pager goes off at 4 in the morning, can't get a hold of the developer, but the person on the pager knows the code base well enough that they'll just go and patch it and bounce the site and fix the issue. Obviously, we'd prefer to not be patching things ourselves at 4 a.m., but still. Also, our team lines are incredibly blurry. I mean, just last week, I patched firmware on my own SSDs because the hardware people weren't easily available. So our team divisions are mostly goal-driven more than permission-driven or anything like that, because it's still a very small operations team overall. And we also make our average engineers be a lot more operationally aware. They all know where our dashboards are. If a database is highly aligned to a team, they're supposed to be very involved in the capacity planning and understanding what the load is going to do. And if they're going to roll out a new feature, we'll have cases where we'll actually make them do all of the site configuration, and we'll just go code review how they're going to reconfigure to add more machines and things like that. So with all of this, what are we building? We're building what you'd probably categorize as a read-mostly site. With the exception of session storage, probably 99% of our requests are read-only requests. We're building physical data centers that we've spec'd out to take millions of requests per minute. And we have very high uptime constraints, being a public-facing website. I'm going to get into this a little bit more. We have no scheduled downtime for read requests, full stop. We are not allowed to schedule downtime for read requests. We will schedule short spurts of putting the site into read-only mode, but those are supposed to total to be about 20 minutes a year. So what does our core site look like? So importantly here, this is not capturing all of my different pieces of infrastructure. This is just kind of the core main thing and the repeatable pattern. I'll talk about a couple of the other patterns that we have elsewhere. So we run with about 160 web servers. And these web servers, like I was saying, we've seen north of 2 million. We did some load tests where we were doing north of 4.7 million HTTP requests a minute. And those 160 web servers are handling all of that. We have some read-only data that we publish from HQ, and that goes up via a trigger-based replication into the data centers. And then we run a service tier, like many people. And our write databases, the vast majority of them, except for some miscellaneous stuff, each write database is owned by a service, which is responsible for kind of consolidating everything down. And we actually run, unlike a lot of people, well, we've had our service infrastructure for much longer before it was the cool thing to have. Our service layer is actually a pretty heavy service layer, as opposed to a lot of people run a light service layer. We have a couple of tricks up our sleeves. We do a lot of in-memory stores. And also to prevent, with the in-memory stores, one of the problems that we ran against scalability is we'll go and in order to deploy code, we'll take out 40 of those web servers at a time, 40 to 60 of those web servers at a time. And the startup queries were super expensive. So we've got a framework now that's basically go run the startup queries, serialize the result sets down to disk, rsync them out. That way all the servers can grab all of that data without running a 5-minute query against, or running the same 5-minute query 60 times in parallel. We also utilize memcache pretty heavily to insulate the read load of our data centers, but we have the databases spec. That way we can lose a few memcache nodes and run the site directly against it. In fact, I believe as of last check, we could run all of the member interaction on the site with no memcache and just run all of that straight back to the Postgres database. Where our technology stack is at the moment, we're in the middle of doing some upgrades. I gave this talk in New York back in April, and I had been saying, oh, we're going to complete this by the end of the summer, but some stuff came up. We're currently moving from 9.1 up to 9.3. We're currently actually getting rid of DRBD. We had been running DRBD back in our 8.4 days. We had done some experiments and done a lot of verification with streaming replication under 9.1 in all of our back office sort of stuff, but we're actually getting there. We're moving to C collation, away from being in ENUS collation just because of glibc likes to keep changing their implementations of character sorting, and that's not great for indexes, especially when you're taking base backups across different versions of OS, different versions of Linux. And also, we had been very much on a model where we were heavily investing in RAM. Now we're putting less money into RAM and more into SSDs. And right now, we're doing cross-data center replication with a custom trigger-based replication. It's based off of some technology. I think there's an open source project on GitHub that's called DB Mirror, but we've rewritten it like 2 or 3 times since then. And then we have some other interesting cases. No one will be happier than me to see the BDR project come and be in core, because I'm certainly ready to get rid of my trigger-based replication. So we do a lot of releases a week. In any given week, we'll do about 15 code releases. And this involves full restart of the site in a rolling fashion, taking servers in and out of the load balancer, doing all those sorts of things. And we also have to make sure that we support schema changes. And we do, on any given week, probably a half-dozen schema changes each week as part of just our normal schema process. And there's a handful of ones that we have to do via data center failovers, but that should get to in just a moment. So, 1 second. One of the big things about running a consumer-facing website is, especially when you're kind of this ad-driven model, is downtime is a big problem. So we spend a lot of infrastructure around being tolerant to almost any type of failure, including data center gets completely unplugged because a certain data center provider did power maintenance and didn't have the redundancy proper. So we currently run in what's called an active passive model. That one data center I showed you is only one of 2 that we have. At any given time, one is taking traffic and the other is inactive. Right now, we are in A. We are in Ashburn right now. So both sites are of equal capacity and capable of taking all of the traffic of the site. And we actually do role reversals between these 2 at least every 3 months. So we will go, we'll all get in a room, we'll go put the site into read-only mode, swap the mastering of our data centers, flush all the data over, swap the mastering around, swap DNS, do all these sorts of things, and in about 5 minutes, we'll be completely live, in production, back in read-write mode on the other side of the country. And we use the second site, obviously, for disaster recovery, but also for load testing. This has actually been, the backup data center has paid for itself in load testing alone. About a year or 2 ago, we started really focusing on doing load tests in earnest and then having someone go and do the methodical process of, all right, I've got this thing, or where's my current bottleneck? Let me remove that. Where's my current bottleneck? Let me remove that. Where's my current bottleneck? Let me remove that. And for about a year to 18 months, we stopped buying servers. when we had been doubling our server footprint about every 2 years. We just stopped buying servers by doing all of the load testing and the bottleneck analysis and those sorts of things. And I'm going to share some of the lessons we learned on the database side as well. And then it's also big for hardware upgrades and schema changes. We can do, because we're in a trigger-based logical replication, certain incredibly invasive schema changes, like changing an int to a long on a table that has 2 billion rows, we can do on one side of the fence and then do on the other side of the fence after we've done a failover. And then we're also, for example, we just bought 96 new web servers for each data center. And we went and took the backup data center, tore it apart, put it back together, and we've got the 96 servers racked in Ashburn, and we're going to wait till we fail over to tear it apart and put the servers into rotation. Our general motto with everything that is disaster recovery is your disaster recovery is not actual disaster recovery until it has been your primary production system. So this is how we will end up facing our databases. This is how we will face our data centers as a whole. That's why the switching is a big part of what we're doing, because every time it is pretty routine to do these switchovers, and we'll go to do the switchover and find that there's something completely broken, and the site wouldn't handle the traffic, or something was wrong with the site. We've gotten a lot better about this before, but we used to have cases where, in order to do the failover, the site wasn't taking the traffic at first, and it would take like 2 hours in order to get caches warmed and all these sorts of things. And we'd rather figure these things out when we have a good data center to fail back to. It's certainly the worst problem, and we've had it once or twice, where you go and you've lost your primary data center, and you go to your secondary data center and figure out that you forgot to provision those extra 4 servers for your search cluster, and all of a sudden you're now production patching while you're dealing with your broken other data center. It's just a total mess. But what this gives us is very little hesitation about switching data centers in the case of an emergency. One person can do this. And we have actually routinely had a couple of cases where one person put the site into read-only mode, failed it over. There's like 4 or 5 hours of mess to clean up afterwards, but it's not user-facing. And in one of the worst cases, like I said, one of our data center providers did power maintenance. We were in production serving traffic in that data center, and lights out in the entire data center. From the time the person responded to the page to the time we were back up again in read-only capacity was about 10 minutes. The ability to just do that and flip the switch and not think twice about it is incredibly important to us. And DR is really treated like production to us. If a server goes down there, it pages just as much as it does in the live site and those sorts of things. Right now, what this means for Postgres is we're stuck in a mix of physical and trigger-based replication until logical is completed. Obviously, when you're doing these sorts of remasterings and these sorts of things, it becomes kind of messy and kind of dangerous to do that with physical replication. And we also need to be able to do no downtime Postgres upgrades, where we're taking writes in one data center and we're doing Postgres version upgrades in the other. So it's going to be great when logical's done, but for now, we're stuck with some trigger-based solutions. But what this also means is we have a really good performance lab for testing all of our read-only workloads. And we've made pretty significant database improvements even before the problems manifest themselves in production, because we'll go and we'll knock over the entire data center and see where it breaks and fix both on the database level and the application level. Unfortunately, we still haven't found a good solution to the read-write workloads, because that's quite a bit harder. We also have development environments that we take all of our databases from production, well, at least everything that doesn't have PII, and dump restore that into 3 different development environments. And just because we're recomposing it onto machines, we're not using base backup at this point, although we kind of want to. because this process is incredibly time-consuming. But it does give our developers very real test environments to work against, because they're working against production data that was live Friday of last week. And every week they know they're going to get exactly the production schema, exactly the production data, and those sorts of things. The PII data is still a little bit messy. We're currently only doing schema there, but we want to get towards generating plausible data that isn't the actual PII and putting that into dev environments. So if you're at this talk, you're probably interested in what are some of the things we've learned from running at these scales. And so I dedicated a significant amount of time to talking about that. First, let's start at the Linux level. Red Hat CentOS kernel versions are a complete lie. If you see, like, CentOS 6 is 2.6.32, they've backported entire subsystems, including memory compaction from 2.6.35. They do a lot of work. They're promising compatibility, but that just because you're on the internet Googling around and Google says that, Linux kernel 2.6.32 doesn't behave this way because it didn't come into 2.6.35, that doesn't mean that that's actually the way your kernel behaves. I don't know. I can't speak to any other Linuxes. This is what we run. One of our big lessons is a no-brainer that kind of fell out of the fact that we didn't have a dedicated database person, and also because some concerns around the way DRBD worked. Really, put your wall, put your data, put your temp space on different physical devices. Even if you're on SSDs and you're like, oh, random I/O doesn't matter. No, they're different resource pools. It's actually, we've seen a massive improvement in stability between running wall and data on separate partitions. Even though they're SSDs and you convince yourself that it doesn't matter, it does in fact matter. Other things, if you haven't thought about the I/O scheduler on your Linux system, again, larger organizations that have someone who knows the kernel probably don't have this problem, it's probably wrong. On older Linuxes, or the default on Linux is the completely fair queue, which is, at least as of our version, completely not recommended to run a database on. We generally, on our data partitions, will run no-op on SSDs and network-attached storage, and deadline on the data partitions of spinning disks. Seen pretty significant I/O improvements off of playing with the I/O scheduler. CFQ does stuff where it'll keep your disk idle because it's trying to optimize for spinning disks. Also, newer versions of CFQ is aware of SSDs, but a lot of RAID controllers report that the RAID array of SSDs is actually of spinning disks. And so you'll find that your kernel is actually spending time trying to order writes in, or order I/O operations in ascending and descending order of logical block order, which doesn't make sense on SSDs, but it's wasting CPU doing that. So definitely SSDs are no-op. You might make a tiny argument for deadline, but I spent about half a day reading the kernel and convinced myself that no-op was just the correct answer. Also, this is one I've happened to see lately. If you run Broadcom network cards and you all of a sudden see that your buffer cache is evaporating, it has to do with free memory and the fragmentation of free memory. It's a bit too complicated to explain here, but if you look at proc buddy info and you see high numbers on the left and really low numbers on the right, this means you're suffering from that sort of problem. It's very particular to network cards that can't do vectorized I/O. For us, one of the other things we discovered, again on physical hardware, is with SSDs, try tuning your RAID controller to be dumber. RAID controllers try to be very clever. And this made sense on spinning disks when they were massively faster than the underlying disks. However, we found that the RAID controller's CPU ends up becoming our disk bottleneck, and that we get significantly higher throughputs by going and basically dumbing down the RAID controller. Don't have it write to its cache, because maintaining its cache and maintaining what it has to write out to dirty blocks is actually far too expensive, and you'll end up getting about half the write throughput. And then don't make it do read-aheads. Postgres is going to do enough read-aheading when it wants, and the computation to figure out if it should do adaptive read-ahead is actually just going to burn you more than just going and doing the reads. That being said, for us, one of the things we discovered, if you run a test fsync, doing this decreases the speeds of fsyncs significantly because you have to go all the way back to the SSD. So we actually run the wall drive in a different configuration than the main data partition. Again, if you're just kind of running stock settings, be very, very careful of dirty ratio. If a certain process writes a lot of temp buffers, say for a temp table or something like that, you can find yourself in cases where you hit the threshold where the kernel decides, well, there's too much dirty. I'm going to do the least reasonable thing possible here and take all of the buffers in the system and write them out synchronously and basically block all I/O on the system until I take dirty buffers down to 0. I've had cases, again, I run high memory configurations where it decided, OK, I've got 120 gigs of dirty buffers. I'm going to sit here for 20 minutes and write them out and block the I/O subsystem. Took our site hard down. Well, at least took the database hard down, I should say. We've got some redundancy there. Other big thing that we've seen recently is check your power settings. We had some problems when we were upgrading from CentOS 5 to CentOS 6 that the system was not respecting power settings, and it was running in performance per watt optimized mode, which is fine if you're on a desktop machine or you're doing sort of ETL-style workloads because your CPU is going to be high. But we found that for low latency operations, the kernel could not catch up with the fact that there was a request fast enough to speed up the CPU clock, and we'd see quadrupling of response times. We'd actually see faster response times when our servers were under higher load and slower response times when our servers were under less load. What's very important here is the kernel stopped respecting the BIOS settings, full stop. You have to very much inspect your, because it thought it knew better. You have to you have to actually check into that. My favorite way to do that is use i7z and actually see if the CPU clocks are spun up and whether or not it's going into deep sleep states. We had to do something hacky, like we write to a file in proc and then leave the program open or something in order to coerce the kernel to always be running at full power. I also highly recommend learning perf. A couple of these things I ended up only being able to figure out and reason about by using the perf tool. It's generally more used by developers, but it's an easy way to get insight into what the system's doing. Are you wasting time inside of your are you wasting time inside of the file system? Are you wasting time at different layers of the system? And you can even end up seeing, if you point it at a backend, you'll see, oh, I happen to be spending all my time building hash maps and do in the middle of the hash join because you can just kind of see what symbols the system is executing. And without perf, I would not have been able to figure out this whole Broadcom network cards making my buffer caches evaporate. Quick aside, people tend to think the OS buffer cache is fast. It really isn't that fast. So fun little test I ended up playing around with at one point. You find a machine with 20 gigs of RAM. You go and use DD to create a 20 gig file. And you just copy dev0 into this big file and just let it sit there. And you wait about 30 seconds. And whatever kernel background ratio is. And then you go to RM the large file, and it takes forever. And you're wondering why. Well, if you actually sit there with like HTOP open, you can watch as it goes for about 10 gigs a second, and as it's scanning buffer cache and just freeing all of the buffers before it allows you to do anything with it. Now, if you do the same thing and instead drop the kernel buffer cache before you do this, files will actually delete immediately. They will be instantaneous. It's actually all the time is being spent in buffer cache. Now, why this is actually relevant for Postgres is if you're doing partition sort of setups, and you're wondering why some of your drop, and you have no other things going on in the system, and you're wondering why a large partition drop is taking a while, If the partition happens to be in memory, you're actually sitting there waiting on the RM of the file for the kernel to free out the buffer cache. You can do things to avoid blocking. We've played with a little and haven't done too much with this, where you actually go, find the underlying files, f-advise them out of memory, and then the drop partition actually happens significantly faster. Caching statements. This was one of our biggest breakthroughs earlier in the year. We use prepared statements everywhere. Mostly, at the time, we were doing it for SQL injection protection. We're in Java, whatever. But when executing many inexpensive queries for the system to do, we ended up seeing that parsing and planning the queries were dominating the CPU time on the database. The queries would complete in 100 microseconds, and they'd spend 300 microseconds parsing and planning. And when you're trying to do 50, 60, 70,000 queries per second on a database, this is a major portion of where our database CPU ended up coming in. We went and, unfortunately, with a 15-year-old code base, it's a little bit hard to say, all right, now everyone make sure that you cache all of your objects. We went into our connection pooling layer and actually were caching statements even if the developers were closing them, just in order to get these performance improvements. And this made a huge difference in terms of our CPU utilization on our databases because the parsing and planning were dominating that. You can get also some of those benefits from using PL/PGSQL functions, as long as network is not your bottleneck. I don't know, a lot of people probably haven't looked at like Wireshark and the Postgres protocol, but when you prepare a statement, you get a description of the result set back in addition to the data, generally. And on single row result sets, especially if you had something that had a lot of nulls in it or something like that, the description of the result set can be as large as or larger than the data row. I had one particular case where I don't know who designed this query, but the result set ended up being larger than the data row. And so doing that sort of solution didn't work in that particular case because it ended up consuming so much more network resources that it wasn't worth it. I do advise also, if you're ever wondering what exactly your application is doing to the database, Wireshark natively speaks the Postgres protocol, and you can see down to these are the select statements. This is what it's caching. This is what it's not caching. And it like breaks out the protocol messages and tells you exactly what's going on there. And for us, one of the main reasons we don't use PG Bouncer, and we've explored this, is in statement and transaction mode, we can't get these caching benefits, and that they basically even out for us. And this one is doing this is slightly better for us than using Bouncer. As for operational issues, our biggest operational issues tend to be around cascading failure. It's not one thing goes wrong. It's one thing goes wrong that triggers another thing that goes wrong that triggers another thing that goes wrong. Particularly, a lot of them are around pooling infrastructure. So this is one of the things we found out of our load test. And it wasn't just at our database connection pool. It was at our service connection pools. It was at our front-end connection pools, all the way up the stack. We had this thing where, all right, we don't want to drop any requests. So we're going to just pool up. If we're running behind, we're just going to queue up all of these requests. So we were doing some things with load tests where we'd go and we'd completely overwhelm the site, crash the site, everything's at 100% CPU, response time has gone to multiple seconds. And we do the thing where we go and stop the load test immediately. And then we were incredibly perplexed because CPU stayed at 100% on all of our systems for another 2 minutes. There were no incoming requests. It was spending all of the time working through its backlog. And this was, sizable problem, obviously, because everything else that's getting into the queue has no utility either, because the user's going to be gone 2 minutes later because you're sitting there waiting for a page to load. You're not going to wait 2 minutes to do that. So one of the main things we did was all of the work queues, both the database connection pool queues and all of these queues, we decided to be much more aggressive about 500ing requests. Because what we found is once you get into these situations of cascading failures, you have two options. You either fail everything, or you fail less than 1% of everything, and then you recover. these changes have taken outages that used to actually take us down, and we have to like bounce services and do lots of intervening work, to recovering before the page gets to the person who's got the pager. They'll go and, oh, there was this thing, and then everyone goes and they're like running to scramble, and they're like, well, it already resolved itself. So we're doing triage at this point and trying to prevent it for next time. And obviously, this is not a substitute for this is not at all a substitute for trying to prevent these sorts of issues, but they're going to happen, and making the site react in a way to try to preserve itself and killing requests in favor of preserving itself is a must. Other big thing, and we haven't done this across the board as much as we want to, is statement timeout. Because we'll often have the case where some query happens to fall into a pathological case. We've got like the support user on our forums for some reason has like 100,000 forum posts, and there's just the code isn't made to handle. Everyone else has 5, and so we have pathological cases, and we'll find that this database will, and then the user will hit refresh, 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 and then you'll now be burning all of your CPU on this one bad request. So statement timeout, having Postgres just kind of opt out and say, screw this, I need to make sure that I preserve my normal operations is important. And this is one of our actual goals for the end of the year, is to separate out our read and write connection pools. Again, we're a read-heavy site, and writes tend to be our causes of cascading failures, either because they get backed up on disk I/O, or they get backed up on a lock because someone decided they were going to DOS attack us and update the same member on 300 concurrent threads, and then all of your connection pools are fighting over the same lock. So what does our standard hardware look like at TripAdvisor? Our old build was a lot of RAM because SSD was super expensive. And so what we did is we would throw between 256 to 768 gigs of RAM. My reviews database is now over at 768 gigs of RAM threshold, and I cluster it every 3 months. It's just massive. But we were servicing all of the queries from in-memory. This made us obviously more vulnerable to write problems, but generally speaking, this configuration worked for us, and we'll do things like, oh, we're going to do a database failover. We go into the data directory. Now there's better utilities for this, but we were using utilities where we'd go and just go, here's the data directory, cat star to dev null to put it into buffer cache, because that's faster than pulling it out at random. Our new build, we're trying to get towards pretty standardized database servers and move load around as opposed to having every database server be a special snowflake. So that's, for us right now, 256 gig of RAM and SSDs. And we're trying very hard, and it's a hard process, especially on the database front, of moving towards server being cattle, not pets. Not this idea of babying a server back to life is a little bit painful. Just take the server out of rotation and re-kickstart it. Right now, our 2 big bottlenecks that we're going to be running into is our kernel version. I end up spending lots of time inside of my kernel. When I do high I/O, I end up spending a lot of kernel time trying to do the I/O, because we're on an older kernel, and we need to move to systemd from system 5 init, and that's just going to be a total mess. The other thing is our databases. We're now able to put some of our databases under workloads where they're doing 800, 900 megabits per second in terms of how many, through 800 or 900 megabits per second of network I/O between doing their streaming replication and answering queries. It's just they're doing lots and lots of network I/O, and the 1 gigabit pipes are not big enough for us right now, are reaching the point where they're not going to be big enough, and we're going to be replacing all of our network infrastructure on our databases up to 10 gigs. I think I'm going a little faster than I had expected. How much time do I have? No, I'm about on time. OK. Have a couple open source things that we want to point out. I have not yet contributed this back up to the OpenSSL core, but I want to. It's just a matter of actually figuring out what OpenSSL's policies are. If you've ever tried to use pSQL and Postgres and debug what's wrong with your SSL certificates, it's very, very, very fiddly if you happen to have gotten it wrong. OpenSSL has this nice utility for everything else called sclient, which you can use for debugging HTTP SSL and Telnet SSL and all the different things. It runs in speaks a bunch of protocols. It doesn't currently speak the Postgres protocol. I got frustrated one evening and stayed up till 3 and added support for the Postgres protocol. I need to push that upstream, but right now, if you go and you just build OpenSSL from that repository, you'll get the debugging utility that can speak Postgres, and it'll tell you everything about the certificate chain, why it rejected the certificate chain, what the certificate, all of the things that you'd actually want in order to be able to debug. Also have a quick and dirty index integrity checker. We had some problems, like I said, with UTF-8 and C collation and all those sorts of things. So this is just, all this does is does index integrity checks to see whether or not your index is actually, your string indexes are properly in sorted order. Also have something that I'm very much thinking about open sourcing. I built it with the intention of open sourcing it, and I want to see now with all these things going on whether or not anyone's actually going to use it or they're just going to use like BDR and everything. We had a use case where we were using Couchbase for session storage because we needed cross data center multi-master. We didn't need the consistency, et cetera. And running that in production was pretty painful. So we decided that we were going to build one on top of Postgres. So we're doing session storage right now. It's meant to be distributed, but then we figured out that Postgres was performant enough that we could do it all on one machine. So right now we're running one machine with this, has more than 600 million user sessions in it. Normally it's doing 2,500 writes a second, can sustain up to 1,500 writes a second. It does multi-master, eventually consistent replication with shards and all these sorts of things. If someone really wants this, come talk to me after this talk, and that might be my incentive to actually do the work there. One of the other ones is, I don't know, how many people here use Carbon or Graphite? OK, so a few people. We're running, I forget which branch, we're running the current stable branch, and we found that it was not particularly stable. So at this point, we've largely rewritten Carbon, but they also went and diverged off from us, and we're trying to decide whether or not we're going to put the effort in. We get, between hardware upgrades and a couple other things, we got like a 10x throughput improvement on Carbon and massive improvements on stability. So if anyone also wants that, come chat with me, and then I'm going to go tell Nathan that he needs to go do that work. All right. Anyways, any questions? That's all I've got, sorry. But
who's your DNS provider?
We have 2 DNS providers. Obviously, you can go and just look that up. I think it's both. What? I think it's Ultra and Dyn. I think it's Ultra and Dyn. I forget which. Because there was the outage, which DNS provider, just about a month and a half ago, where one of the major internet DNS providers went down. It was one of ours, but there were other sites that were just hard down.
Have you thought of using BGP to do flashing?
BGP to do the
rerouting on the data center level?
I forgot to repeat the question. He first asked what our DNS provider was, and then he was asking about using BGP to do the rerouting. We've put actually some thought into that. At the moment, that hasn't been our biggest bottleneck in the failover process, so we haven't invested that much into it. Using BGP for that is actually one of the things we've discussed. We actually, even now, we run our own WAN, so all of the network, even if you're going to hit our other data center, if you're closer to this one, you're going to end up going in that data center and across our network. But the biggest thing with that is we'd have to kill in-flight requests, right? Because you're now repointing, or there's problems with going and repointing to a different load balancer. So we've played around with that idea, and the biggest concern there is we'd kill all the, at least as far as we can see. I'm not obviously a network engineer. We'd kill all the in-flight requests, and that was a bit concerning for us. Other questions?
Are you guys doing automatic master failover?
Automatic master failover. Question is, am I doing automatic master failover? What do you mean by that?
So let's say if your master database goes down, what do you do?
We page someone. So to be to be completely honest, we had done some stuff. We used to do automatic database failover, and the rate at which we had actual database failovers versus the rate at which the automatic database failover would trigger by itself and leave the server split-brained or do any of those sorts of things made it just, I mean, trying to think of, there's been about one time in the past 5 or 6 years that we've had a master go hard down, right? So it's a pretty rare occurrence, whereas we had, like, within 6 months, 4 or 5 times where the automatic failover decided it was going to bring the master hard down. We think that we do need to invest more into doing that right, because it's a very fiddly thing and you have to do it right. But at the moment, it just hasn't been a high enough priority versus all of the other things to get right for us. You have a question?
Yeah, I have 2 scale questions. The first one is regarding like shared buffers. Do you stick to the 1 to 3 rule on the file system, or do you just make a really large shared buffer? Second question is on partitioning. Do you have any large tables with, like, say, 1,000 partitions by date, and that works okay?
OK, so let's go question by question. Your first question was around the 1 to 3 rule. What's the 1 to 3 rule? I'm not.
So it's like typically it's advised that the memory that you dedicate to your shared buffers is one third of the available physical memory, and then you leave the other 2/3 in the file system cache.
So we had been going closer to, or we had actually been doing basically that. I generally heard a quarter, but close enough. And we were playing around with that, and we actually found, we ended up going back towards what a lot of people do, which is more, after a certain point, stick with like about 4 to 8 gigs of shared buffers, because the inefficiencies in shared buffers, particularly we'd run into cases where you'd get one, because I don't know how much you know about the clock inside there. The clock would end up sweeping so slow that certain tables would all get pinned at 5 utilization, and therefore we'd have random database freezes where these blocks of everything at level 5, where other queries were just like, I need 5 shared buffers. And it would just sit there trudging through shared buffers trying to find something that it could use. So we know that on some ways, it's a little worse to be the smaller shared buffers. But in order to keep the clock sweeping fast enough, that was basically the main argument. I did a lightning round talk in New York City where I have some slides where I actually I drew some graphs and some pictures of what happens in an unhealthy shared buffer sort of situation, and keeping it smaller was important for us. As for partitions, I have tables with hundreds of partitions, and that kind of works well for ETL workloads. I have heard to avoid thousands of partitions, but I haven't actually tried there. We have, particularly in our analytics for like site health, not for like business analytics, but our site health analytics, we run that through a Postgres database. And we have like a hierarchy of partitions, but very often the queries were targeted at subsets of that hierarchy of partitions, so wasn't as much of a problem there. But I believe there was a bug that was patched in 9.3.4, 9.3.3 about things not passing down, the optimizer not passing down through union alls properly, and it's a bit better there now. All right. You?
How do you keep your source cluster in sync with your database? Do you have a Kafka-like setup, or?
No, it's much sadder than that. We just, We accept the fact that our search indexes are not up to date, and we just do full rebuilds on a routine basis. We kind of want to do the Kafka-style thing. We've actually had a lot of problems with Elasticsearch, to be completely honest, and so doing full index rebuilds has been smoother for us, and we haven't put much effort into trying to figure out how to do some of the other things.
Yeah, in your service-oriented databases, is there data that's kind of shared between all those, and like how do you keep that in sync?
It tends to be completely sharded. There are a few edge cases where we'll occasionally have it do funny things like services calling services. We try to avoid that. We try to actually make the client sort of synchronize those sorts of things. And when we can, we just have them apply data in an order that would make sense, like never write the review before the member is there and those sorts of things. Again, be completely honest, we don't handle it as well as we should. Other questions? Yes, Josh.
I'd like to see open source PG Global KV.
All right. Sure. OK. I think we are almost out of time. I probably can take one more question, and then you can come find me afterwards. Yes?
I have one small question. So how many servers do you have, and how do you handle the failover to the other data centers when you have update all the services you have?
So a couple things. How many services or how many servers? How many services? He asked how many services we have. We have like probably half a dozen really critical ones and maybe 18 to 24 total. And one of the things we end up doing is we do one of two things when we're doing this failover style architecture. One of them that we do is just once all the data is replicated, just clear memcache. We just drop memcache on the floor and say start over, because the databases don't actually, the databases can pretty easily absorb the load. The memcache is there for spikes. The other one that we do, which is a little bit more complicated and we should revisit at some point, is the receiving servers actually have triggers, or the receiving databases have triggers on them, which is a queue of things that need to be cleaned up in the services and in memcache. And we have processes that run that go ahead, consume the queue of things that they need to clean up, and then they'll go and they'll invalidate memcache, and they'll patch up the services and do all those sorts of things in the same way that the services themselves normally do it with each other. It just goes and says, well, this record is invalid, clear it out. Because our biggest thing is we're perfectly fine clearing stuff out of caches. I only need like an 80% hit rate, right? So it just goes and says, delete this from cache, and then we'll hit it back when we the next time a user requests it.
Do you have any kind of network infrastructure, 24-hour network infrastructure, where people are awake 24 hours?
Not really. I mean, we have right now, we have an operations person in Ireland and one in and most of our stuff in Massachusetts. Obviously our stuff pages, but most of it's actually pretty stable in that regard, and we haven't had to do that sort of thing. Particularly our physical operations team, the manager doesn't want to spread that out, and so that entirely runs in our HQ. And we do a lot of things in our remote data centers with remote hands. All right, cool. Looks like that's about all the time we've got. Thank you all for coming.